Hello and welcome to the fourth episode in the Network Defense series. And in this particular episode, the last one, we'll explore some related concepts to network security, and we'll take a look at in which direction many enterprise networks might be evolving over time. So one of the concerns that a security person often has when it comes to the use of virtualization technology is that of network visibility. But first, let's take a look at what virtualization means. We use it all the time. Most of the systems that we connect to are not necessarily running directly on hardware. Of course, all of them eventually are. Even cloud computing is just hardware in someone else's data center. But the key aspect of what makes virtualization special is that there is a layer of abstraction between the hardware and the operating system. And that's an important one, because even now when you look at your own computer, for example, and you open, depending on the OS you have, maybe your task manager or your activity manager, or you run top or PS, you'll see that most of the time your computer is sitting idle. It's not doing a whole lot. The processor typically hovers around maybe 1% utilization, maybe 2%. You have multiple processors or at least multiple cores. Your memory doesn't fill up. And all of that is really a waste of resources. We need to have these highly overspecified computers to accommodate for peak utilization, but not necessarily for everyday utilization. And that's where virtualization steps in by basically segmenting up your hardware into different pieces of virtual hardware. And so if we look at the image here on screen, we'll see that in a traditional architecture we have the computer's hardware. On the hardware we run the operating system, and within the operating system we run applications. It means that all of the applications together share a single operating system, and the OS maps directly to the hardware. In a virtualized world, that's no longer the case. The applications still match to an operating system, and each application is still part of only one operating system, or I should say each running application. But rather than mapping directly to the hardware, the OSs map to a virtualization layer, sometimes called a hypervisor. And that means that the hardware is now able to run multiple operating systems at the same time. They don't all have to be the same operating system. For example, I am recording this on my MacBook Pro. That's an Apple device. But I have virtual machines running for Linux and for Windows on here as well. And that means that effectively my operating system my hardware, I should say, is running 3 operating systems plus a virtualization layer. It also led to a completely new way of IT operations, because now I can easily copy and paste virtual machines, because in the end now they're just a file. And that means I can very quickly spin up a new device, or maybe change some settings where before I may have had to order extra memory or extra disk space. In a virtualized environment, I can all do that through a console or a command line. From a security perspective, there are some concerns with that. We want to minimize our trust surface, so we don't really want to spin up unlimited number of operating systems, because then each of those operating systems needs to be patched, configured, and maintained. It also means that we have a lot more visibility issues, and especially when it comes to devices, virtual devices within the virtualization infrastructure communicating with each other. Now that's one of the issues. There are of course others. So first of all, I mentioned that ease of deployment that leads to spinning up multiple OSs very quickly. That is a maintenance issue. But the other problem is if a guest OS, one of those virtualized operating systems, escapes the sandbox. In other words, they're able to communicate directly with that virtualization layer, they might be able to attack other virtual machines on the same hardware as well, and that would be an issue. Same thing I mentioned before, if we have multiple virtual machines communicating with each other within the same virtualization infrastructure, that never hits the physical network. So all of my intrusion detection systems and firewalls will be ineffective unless I also virtualize those, or if I start reconfiguring my network architecture to accommodate for that. And so all of those issues lead to concerns, but there are so many benefits to the use of virtualization that we're dealing with it. We're accommodating for the use of deployment, the use of spinning down, the scalability, and all of the benefits that we're getting from virtualization, but virtualization does lead to different security requirements. Containers are a different form of virtualization. Only this time it's not the operating system that we're virtualizing. I should say it's not the hardware that we're virtualizing. It is access to the operating system that we are regulating. So in a container-based application, we have the common hardware, we have the common operating system, and then we have a virtualization layer, where each application can still access the host OS and still has access to the resources there. But it is completely self-contained. Within a container, there is no access outside of that container other than via predefined network connections. From a security perspective, containers and virtualization have many the same problems. If anything, in container technology, it's a little bit amplified because it's even easier to spin up a container. If we don't have to redeploy the entire operating system for each virtual machine, we're only redeploying the application and the application's runtime environment. And that, of course, is much easier than to do a full OS. So on the one hand, we get easier maintenance, we get easier standards to baselines, but on the other hand, we get increased complexity by the sheer volume of these containers that might be running at any single point in time. So the ease of deployment may lead to less ability to manage. Also leads to abandoned systems where a sysadmin or a developer might spin up a virtual machine, or a container I should say, just to test something and then forget to deprovision it. Because there is so little overhead with one of those containers, that's a real risk, and we see that happening quite frequently in reality. The infrastructure becomes a lot more complex. Instead of dealing with a single system that's talking to a single other system, there's a lot of fragmentation happening now. And just like with virtual machines, if we can break out of our container, we have access to the operating system or to other containers. And networking and network visibility, of course, is still a concern as well. Virtualization and containerization are logical steps in moving away from physical hardware in a data center on-premise. About the same time that virtualization started to become very popular, cloud computing started taking off as well. Cloud computing really makes life easier for many businesses where they don't have to maintain their own data centers anymore. Maintaining a data center is complex, it's difficult, and it's expensive. All of those computers require power, and that means that there has to be a lot of power being brought into those data centers. But computers are also fairly inefficient, which means that they generate a lot of heat. And to counter for that heat, we have to bring in air conditioning, which takes more power. With that air conditioning, now we have the concern that everything is in a single location. So now fire safety becomes an issue. So the specialized fire safety situations, we need to have specialized access controls, and we need to have backup power. So running a data center is actually a very expensive operation. And if I can have someone else do that for me, more power to me. I can make them specialize on running the data center, and I specialize on running my core business. That's how data centers started, as outsourcing capabilities. The other part is then, well, if my computers are in someone else's data center, do I still have to have my own computers? Or can I rent those as well? Or maybe knowing that virtualization and containers exist, maybe I don't want to buy my own computers. I just want to buy some space on one of those virtual machine infrastructures or in a container infrastructure. And that's really where cloud computing became very, very strong, is by renting out space on those virtual machines to companies who needed them. And that means that now, as we're talking about cloud computing, that's really what's happening most of the time, where we're renting time on someone else's computer in someone else's data center. So we have to have a couple of criteria before we can really call it cloud computing, rather than just outsourcing. The first criterion is that the service must be available on demand and through self-service. If I have to start negotiating and I need to have a lot of effort and I need to sign contracts and all of that kind of stuff, then, in the pure definition, it's not really cloud computing. I need to be able to do that myself. Like, here's a credit card, put in the number, and within a very short, reasonable amount of time, I should have a virtual machine up and running. The other part that makes cloud computing interesting is that we only pay as we use or pay as we go. Before, if I would have to buy a new computer, I would have to overspec it, and I would have to specify it for such a time that I could expect to get 4 or 5 years of runtime out of it. I don't really care anymore for cloud computing. I'll start paying when I need it, and I'll stop paying when I don't. It shifts the burden of having to buy upfront physical capital hardware from the company that uses it to the company that provides it as a service. And from a business perspective, that's very interesting. But it also comes with risks. The self-service component means that IT departments can be bypassed. And this is something we see every single day in practice. Almost every cloud service provider will start calling entities in the business and say, you don't need IT. Just don't talk to them because they just slow things down. You can do this yourself. Now, the problem is that information technology, IT, is much more about the I, information, than it is about T, the technology. It's all about knowing what information you have, how to use that information, how to make sure it stays correct and it's correctly regulated access, to make sure that it is accessible at the right time. And self-service options often bypass that, where people have done the next finish thing on their own Windows PC, and now they think that they are system administrators. Unfortunately, IT is much more than that. It is much more of a process-based discipline than a technology-based discipline. It also means that if I am going to run my servers or services in someone else's data center, my firewalls and my intrusion detection systems don't see it anymore. Their firewalls and their intrusion detection systems might, but mine won't, because that's not where the data is anymore. And so I lose some visibility, or actually quite a bit of visibility, into what's going on. Regulatory compliance might become an issue. Sometimes there are laws and rules that require us to have certain controls in place, and if I don't have them or I can't prove that I have them, I might be in trouble. So now I have to work with my cloud service provider to make sure that they have them and that they attest to them. Investigations and forensics might become an issue. I still have access to the virtual machine, maybe, depending on the model I use, but I don't necessarily have access to the raw data anymore, and especially not to the hardware or the data center. And of course, all the risks of virtualization and containers play a role as well. And these are additional risks, but the benefits are so great that we take these risks and we try to do our best with them as we can. Cloud computing can be made available via 3 mechanisms. One, infrastructure as a service, and basically that's virtual hardware. The client is responsible for all system administration. The service provider basically hands over a running virtual machine with an operating system on it, and it's your job to make sure the operating system stays patched and configured and used appropriately. It's the most readily available form of cloud computing, and almost all cloud computing providers offer this service. Google through their Compute Engine does it, Amazon through their web services, Microsoft through Azure, and there are many others. One layer more complex is where I don't want to deal with system administration tasks anymore. I just want to deploy my applications and run them. And that's called platform as a service. At that point, the service provider will run the OS for you. The service provider will make sure the hardware stays up and running, but you're still responsible for deploying your own software to that platform as a service infrastructure. Gives you some more control, especially when it comes to custom-based software development. So it's an interesting option for companies who heavily rely on that. And then the last one is by far the most popular one, is software as a service, where I don't even want to know what operating system is running or how the programs work. I just want to use those programs. And that means that the service provider does everything, but I gain access to the service as a whole. Now, as we go from infrastructure through platform to software, I have to do less myself as a client, but it also means that I can do less as a client, which means that from a security perspective, I lose visibility and I lose control. That's not necessarily the end of the world. We can do a lot of that through contracts, but it is something to be aware of. Clouds can be everywhere. We can have a private cloud, which means that it's mine and only mine. If I want to share it, that's fine, but that's up to me. I still have a lot of the benefits of rapid deployment, flexibility, and all of that stuff that I would have when I rent out from a commercial service provider. So there's still a lot of overhead, but I do get a lot of the benefits. The other one, a public cloud, that's what typically, when you think about Amazon, Google, and Microsoft Azure is, where anyone can sign up. And it's the cheapest alternative because you're sharing the same hardware and maybe even the same OS with other clients. And that's not always acceptable from a risk perspective. So we have community clouds. And those are kind of a hybrid between public and private. Are those environments where a group of organizations work together. So for example, the government might do that, or healthcare providers might do that, where they say, listen, we're all subject to the same rules and regulations. Let's build an infrastructure that meets those, and then we'll divvy it up amongst ourselves, and we'll rent space from this conglomerate. And of course, you can go any way, shape, or combination, and that's called a hybrid cloud. So the key takeaway is, though, that we have less visibility and we can exercise less control in a virtualized environment. All of that security needs to be built in to the contract that we sign with the service provider. And that means that the security role starts shifting to things like governance, compliance, availability, data security, identity and access management, and disaster recovery and business continuity planning. What happens when your service provider, for example, doesn't want to do business with you or goes out of business? Do you get your data back? Do you have an alternate process in place? All of those are concerns that we really didn't have when we had everything in-house. In the Internet of Things, there was a lot of change. So first of all, what is the IoT? The Internet of Things is a combination between the physical world and the virtual world of the Internet. Up to the IoT, things were either software or things were hardware. And there was really no bridging the two. Now we see that happening more and more often. Cameras are internet-enabled. Thermostats are internet-enabled. Refrigerators are internet-enabled. But when you really boil that down to its bare essence, at that point you can say, well, what we see interacting with the real world, software and hardware components, are sensors that collect the data and process it through cloud computing typically, but that can then trigger actuators. For example, if I have one of those Nest thermostats, there's a sensor in that Nest thermostat that tells a computer how warm it is. That temperature is being uploaded to the cloud and compared against what I want it to be. And the cloud computing resources will trigger my heating system and say, okay, you need to go on because it's too cold in the house. And when it's warm enough, they might say, well, now you can turn off again. Those are called actuators. But it also means that there's going to be a lot of devices that are interconnecting, all kinds of data streams going all over the place, and that means complexity. And complexity is always the enemy of security. The other part is that those devices have to be cheap. People don't want to pay money for them, and cheap means that we're taking shortcuts. And that means that we're not using cryptography when we should be using it, for example. It means that we don't have an update mechanism in place to push out new patches to these IoT devices. And it basically means that we're back to the world of the IBM PC in the 1980s, where every computer was self-contained and hard to update. And now we're struggling with trying to figure out how we can scale that back up to an acceptable level. And so software updates is an important one. Data collection and upload to the cloud is concerning in some cases, depending on what kind of data we're uploading. Do we really want a webcam to be constantly streaming the room that we have it in? Let's say you're a parent and it's your little child's, your baby's bedroom that you have a nanny cam in. Maybe that's not exactly what you thought of, that now all of a sudden some service provider can be watching your kid all day long. And of course those devices themselves must also be securely built and configured. And we saw this a while ago, and it keeps on coming back. But the Mirai botnet in 2016 created a large distributed denial of service attack, and the main reason was because the devices had hard-coded built-in credentials that could not be changed. So people took shortcuts, and those shortcuts came back and really hurt the internet as a whole at that point. The last trend that's worth mentioning is deparameterization. I can say this. And that means that we are shifting from, well, the firewall is protecting everything to, well, the firewall isn't really protecting anything, because my mobile users, and like we are today, for example, in this Corona era, we're all working from home and we're accessing cloud services. My firewall is nowhere in that picture. The only time that traffic would come through my firewall if it's that people are either on campus, which no one should be, or secondly, if we are accessing resources that are on campus, which is very limited at the moment because we put a lot of our stuff in the cloud. And at that point, our IDS and our IPS doesn't really help much. They just don't see anything. And so if we're looking at this, we're seeing that, let's go with my enterprise setup here. You know, there's almost no internal servers left over here, so my IDS isn't really seeing much. My firewall might be limiting traffic to or from internet servers or to or from the internet, but they're not going through my firewall, they're just bypassing things. And all of that becomes an issue. So how do we deal with that? How do we re-engineer that infrastructure? And that means that we need to make sure that we use strong transport layer encryptions, TLS, most of the time. Wherever we can, we have to make sure that we authenticate all the parties in a communication. We have to really pay attention to the contracts that we sign with our service providers. It's a very different game in a mobile, deparameterized world than it is when I have a physical infrastructure on campus. And that is now known as zero trust networking, where the idea is that all networks are hostile all the time. It doesn't matter that you're on the internet or at home or at work, there will always be an intruder around, which ties in very closely to the idea of threat hunting. And so some of the things we can do is everyone and everything must authenticate. Whatever we can to authenticate, use the strongest form of cryptography that we have available. Figure out who someone is rather than where they are. Just the fact that you happen to be on campus isn't good enough anymore to gain access. I need to know who you are so I can give you the appropriate level of access. And still, all activity must be logged, analyzed, and if we see anomalies, responded to. It's a very changing world at the moment for cybersecurity folks, but it doesn't mean that the foundations of what we saw, you still have to develop secure software. We still want to make sure that our websites are not vulnerable to SQL injection or cross-site scripting. We still want to make sure that our software doesn't have buffer overflows in them. But the complexity goes up. and especially the complexity of the environment in which all of this stuff is deployed. That concludes our talk about network defense. We discussed a lot of different things, technologies, traditional technologies, architectures, and some of the future trends that are coming. I hope it was interesting.